Here's a solution to one of the problems from section 4.7 on L'Hopital's rule. We're asked to compare the growth rates of two functions, and so we talked about the fact that that means that we're trying to compute the limit as x goes to infinity of the ratio of these two functions. So let me just refer to the first one as f of x and the second one as g of x. And so I want to look at the ratio of f of x over g of x. Now, just to make it clear, they're using a little bit of weird notation here, or at least notation that I personally don't like. So f of x is the log of the square root of x. And I would put the parentheses around it because otherwise it's hard to parse. And the g of x is really log of x all squared. So that would be my preferred way of writing it. Makes it a little bit easier to see what's going on. So there is something to this because there is a log property that you can use to simplify this right off the bat. And I think it's probably worthwhile reminding you of, because anytime there's something inside of a log, you can use this and it will definitely save you time. So the logarithm rule that helps here, this is not a derivative rule, this is just a rewrite before we really start doing anything. The log rule is that when you have the log of something to a power, then that power can come outside. So in this one, the denominator is not log of something to a power, it's a power of log. So that is not does not match at all, but the numerator does. This square root of x that's in here, that's really x to the 1/2 power inside. So this rule means that the natural log of the square root of x is really just 1/2 times log of x. The x to the 1/2 power on the inside of the log can be separated so that the 1/2 comes outside. So that's a weird rule, but that is a rule of logarithms, and that will help you in these problems. Now you don't get overzealous and use it when it doesn't apply, as in the denominator here. This is not log of something to a power, right? It's got logs and powers in it, but it does not match up with that. All right, but we don't need it. As long as one or the other simplifies, we're in good shape. So the limit as x goes to infinity, in the numerator, I have 1/2 log of x. And the denominator, that's log x squared. So that's log x times log x. And so you can see that one factor of log x will cancel the numerator and denominator. And so I have the limit as x goes to infinity of 1/2 in the numerator over log x in the denominator. And so this is not an indeterminate form. The numerator is 1/2. The numerator is not infinity, but the denominator is going to infinity. So I have a constant divided by something that's growing without bound. So when I have a constant over something going to infinity, that's just equal to 0. So it turns out that because of this handy rule of logs to apply, I don't need L'Hopital's rule at all. If you do apply L'Hopital's rule to this, it would be totally fine to do that. You're going to end up with a chain rule here with the log of something and a chain rule here of something squared. And so it's not the worst thing in the world, but you can see that that's the derivative of this divided by the derivative of this is going to get a little bit involved. Anyway, this may seem like a trick, but this is an important property of logarithms, and this is one place where it shows that it's valuable to know.